Welcome to this learning module. Today, we'll be exploring runoff characteristics and their associated event mean concentration, or EMC, values. This module aims to provide you with a comprehensive understanding of how different land uses influence runoff quality and the significance of EMC values in water quality assessment. Today, we'll explore key concepts related to land use classifications and their associated event mean concentrations, or EMCs. Our focus will be on understanding runoff characteristics and how they tie into these concentrations. We'll delve into what an event mean concentration is, recognizing that EMC data are derived from field sampling and provide valuable insights into average annual values. Critically, we'll also look at how the 2024 Applicant's Handbook specifies these EMC values for common land use classifications, which are essential for use in permit applications and can be found in Table 9.2 of that volume. Runoff concentrations are known for their high degree of variability. This isn't just a minor fluctuation. It's a significant characteristic that changes both from one rain event to the next, and even during a single storm event itself. This variability is driven by several factors, including the intensity and frequency of rainfall, the specific soil types in an area, the dominant land use, and even the intensity of that land use. Broader weather patterns also play a role. Because of this inherent variability, it's absolutely crucial that any monitoring protocol designed for runoff collection accounts for these fluctuations. This is the only way to accurately determine representative annual event mean concentration, or EMC, values. Failing to capture this variability would lead to an unrepresentative average. It's important to note that published data, such as that from the National Pollution Discharge Elimination System, or NPDES, should generally not be used if you're trying to determine an annual average EMC. These data typically reflect runoff characteristics for specific rain event conditions and are not designed to give you a yearly average. However, NPDES data can be quite useful for comparing different sites because the collection methods are standardized, allowing for a consistent basis of comparison across locations. Runoff characteristics are crucial inputs for many engineering analyses. They are essential for conducting pollutant loading analyses, performing total maximum daily load or TMDL calculations, and evaluating pre- and post-development pollutant loadings for various projects. When we talk about runoff concentrations, they are typically expressed as an event mean concentration, or EMC. An EMC is essentially the pollutant load from a specific runoff event divided by the total runoff volume from that same event. It's important to use suitable conversion factors to ensure your measurement units are consistent. To determine an annual EMC value, we evaluate individual event EMC values collected over a range of rainfall depths and across different seasons throughout the year. These values are generally determined based on field monitoring, which usually requires collecting data from a minimum of 7 to 10 separate events to capture a representative range of conditions. Once we have a reliable annual EMC, we can then calculate annual mass loadings. This calculation combines the annual runoff volume with the annual EMC to give us the total mass of a pollutant carried by runoff over a year. So, the annual mass loading is simply the product of the annual runoff volume and the annual event mean concentration. These calculations are often performed using spreadsheets or specialized environmental software. Here, we're looking at an example of calculating an event mean concentration, or EMC, specifically for total nitrogen from a highway land use. The core idea is to collect enough samples throughout the year to accurately represent the frequency distribution of rain volume. This includes ensuring that your samples capture events where the rain volume is greater than, say, 1 inch, which might occur about 10% of the time, and that you have at least one sample from each season. In this particular scenario, 20 samples were initially taken. However, 10 of these samples were ultimately not used, either because the rain volume was insufficient, meaning it simply didn't rain enough to get a representative sample, or due to various collection and laboratory measurement difficulties. As you can see from the graphs, we plot the running average for each sample. This allows us to observe how the EMC stabilizes over time. What we're looking for is when the change in this running average becomes acceptably small. In this case, for the 8th, 9th, and 10th samples, the change in the EMC, or the average value compared to the previous ones, did not vary by more than 5%. We technically could have concluded our sampling after the 8th sample, but we chose to include all 10 to ensure that we had at least one sample representing each season, and also one that captured the effects of a long dry period between rain events. It's also worth noting that if you compare this highway total nitrogen EMC to the values in Table 9.2 of the AH, you'll find it's very consistent, showing 1.24 versus 1.25 for this specific type of highway and traffic volume. The original database for Florida's runoff characteristics was developed in 1990 by Environmental Research and Design, primarily to support the Tampa Bay Swim Plan. To build this database, a comprehensive literature review was undertaken to identify runoff event mean concentration, or EMC, values specifically for single land use categories across Florida. Approximately 100 studies were initially identified, and each of these was rigorously evaluated based on several criteria: the adequacy of the data, the length of the study, the number of monitored events, the completeness of the data set, and the specific monitoring protocols used. The original selection criteria were quite stringent. A critical and often most difficult criterion was that the monitoring site had to represent a single land use category. Additionally, studies needed to include at least 1 year of data collection, with a minimum of 5 events monitored in a flow-weighted fashion. The monitored events also had to cover a wide range of rainfall depths and antecedent dry periods, and the samples needed to reflect seasonal variability. After this thorough evaluation process, approximately 40 studies were ultimately selected for inclusion in the database. The EMC values from these studies were then summarized by general land use category. This effort resulted in the first known compilation of EMC data specifically for Florida, and the EMC values themselves were calculated as simple arithmetic means. Based on an extensive literature survey, a set of common land use categories was developed. These categories were created specifically because of their similarities in anticipated runoff characteristics. We classified them into 2 main groups: pre-development and post-development. Our original database provided sufficient data to establish specific event mean concentration, or EMC, values for 5 distinct pre-development categories and 7 post-development categories. The pre-development categories included land uses such as agriculture, encompassing pastures, citrus groves, and row crops, along with open spaces, forests, mining areas, wetlands, and open bodies of water like lakes. For post-development scenarios, the categories included low-density residential, single-family residential, multifamily residential, low-intensity commercial, high-intensity commercial, industrial areas, and highways. This categorization allowed for a more consistent and accurate analysis of runoff characteristics across different land use types. When characterizing runoff water quality, the measures we most frequently see reported in impact studies are typically solids, total nutrients, and metals. For these parameters, it's generally total species concentrations that are documented and analyzed, largely because the majority of environmental regulations consider these total concentrations when assessing water quality. Beyond the basic flow and volume measurements, other critical water quality parameters were also documented, primarily within urban environments. Notable among these are biological oxygen demand, or BOD, chemical oxygen demand, or COD, and measurements for oil and grease. Additionally, parameters like total and fecal coliforms, as well as E. coli, were often recorded to assess bacterial contamination. However, it's important to note that the data available for these specific parameters is generally more limited compared to other runoff characteristics. Here, we're looking at the land use categories recognized specifically in Environmental Resource Permit, or ERP, applications. It's important to understand these definitions as they guide many environmental regulations. Let's break them down. Low-density residential, or LDR, describes rural residential areas with less than one dwelling unit per acre. Single-family residential, or SFR, refers to typical detached family homes on lots smaller than 1 acre, and can also include duplexes on slightly larger lots and even golf courses. Multifamily residential, or MFR, encompasses residential units like apartments, condominiums, and cluster homes. Moving to commercial uses, low-intensity commercial, or LIC, are areas characterized by low traffic levels where cars might be parked for extended periods. Examples include schools, office parks, and smaller shopping centers. In contrast, high-intensity commercial, or HIC, involves areas with very high traffic volumes, such as downtown districts, large malls, and major commercial office complexes. Industrial, or IND, land use covers manufacturing, shipping and transportation services, and municipal treatment plants. Highway, or HW, refers to major road systems and their associated rights-of-way, including interstates and major arterial roads. Agriculture, or AG, broadly includes activities like cattle grazing, row crops, citrus groves, and other general agricultural practices. Recreation, open space covers parks, ball fields, and general open or barren land, but note that it specifically excludes golf courses, which fall under single-family residential. Finally, mining, or M, refers to general mining activities for materials such as sand, lime rock, or gravel. It's crucial to understand that these particular categories were developed based on similarities in runoff EMC values for environmental modeling and may not always correspond directly to other land use classification systems you might encounter, such as FLUCCS codes or property appraiser databases. In October of 1994, Environmental Research and Design, commonly known as ERD, published a significant summary of runoff data. This publication built upon the results collected as part of the Tampa Bay SWIM study and was supplemented with new data to continue documenting concentration levels, a process that began in the early 1990s. Titled Stormwater Loading Rate Parameters for Central and South Florida, this work was crucial. It not only included all the data from the 1990 collection effort, but also added loading rate information specifically for highway and transportation land uses. Furthermore, it refined the categorization of agriculture, dividing it into pasture, citrus, row crops, and general agriculture, and included new references for previously defined land uses. A notable addition was the inclusion of event mean concentration, or EMC, values for wetlands, based on available existing wetland data for Central and South Florida. Specific values provided were 0.10 milligrams per liter for total phosphorus and 1.00 milligram per liter for total nitrogen. The publication also introduced and included aerial loading rates for stormwater parameters, expressed in kilograms per acre per year. However, it's important to note that ERD no longer supports this specific aerial loading methodology. When we look at the summary of runoff characterization studies, the number of sites where we've collected EMC data is a direct reflection of the activity in those specific areas. This comprehensive data set draws from a variety of sources, many of which were meticulously documented by Harper in 2007. For instance, we found that only one mining area was adequately documented and available for our sampling efforts. Similarly, until about 2012, the EMC data we had for undeveloped land areas was quite limited. The method mentioned here, where certain values are calculated as a mean of single-family residential and undeveloped land, illustrates one way we synthesize these diverse datasets. It's important to note that these figures have been supplemented with much newer data, and the latest changes are fully reflected in Table 9.2 of the applicant's Handbook Volume 1. Here, we're looking at data derived from 17 different studies, all contributing to our characterization of runoff originating from single-family residential properties. This characterization covered a range of important parameters, including nutrients, biochemical oxygen demand, or BOD, total suspended solids, or TSS, and various metals, with all of this information being compiled for the 2007 ERD report. I want to draw your attention specifically to the lead concentrations that are highlighted in yellow. These particular measurements come from studies that were conducted before lead was removed from gasoline. What's evident from the data is a rapid and significant decrease in lead concentrations once that change in gasoline composition took place. Our focus here is on understanding commercial runoff data. The information we'll be discussing was derived from specific characterization studies, both low and high intensity, designed to analyze runoff from commercial areas. These studies were crucial for generating the event mean concentration, or EMC, values that were compiled for the 2007 report. Here we're looking at the highway runoff characterization data, specifically from 15 different studies indicated by the N equals 15. These studies were used to develop event mean concentration, or EMC, values for highway runoff. It's particularly interesting to note the substantial reductions we've seen in lead concentrations over time. Furthermore, it's important to understand that the most recent EMC values for highways are actually even lower than those calculated and summarized in this particular data set. To determine the average annual mass loadings, you'll take the event mean concentration, or EMC values, and multiply them by the annual runoff volume. It's important to note that the published EMC data for 23 specific land uses in Florida can be found in the Applicant's Handbook, Volume 1, Table 9.2, and these are the values that must be used in all permit applications. While the calculation itself is straightforward, software can be extremely helpful in accurately determining these average annual mass loadings. BMPFast is one such software that not only provides accurate loading calculations, but also allows for complex scenarios, like calculating composite loadings for multiple land uses. It even includes a user-defined option, so you can input EMC data that might not be pre-loaded into the software. Here, we're looking at a comparison of developed land use event mean concentration, or EMC, values. This analysis contrasts data from a previously developed statewide EMC database with the values found in the Applicant's Handbook. What we found is that nitrogen concentrations listed in Volume 1 of the Applicant's Handbook are generally lower than those in the statewide EMC database for 5 out of the 7 land types reviewed. Total phosphorus concentrations, however, appear to be quite similar between the two sources. A specific note of interest is that highway EMCs are lower in the Applicant's Handbook for both total nitrogen and total phosphorus. This comparison highlights the dynamic nature of these values, emphasizing that as changes and updates occur, the software or spreadsheet calculators we use must be adaptable to incorporate these new figures. To address this, tools like the BMPFast software already include an option for users to define and input their own specific data, allowing for greater flexibility and accuracy. This slide illustrates the typical total nitrogen concentrations we observe in stormwater runoff across various land uses. A crucial point here is that all developed land uses, whether agricultural or urban, exhibit significantly higher nitrogen concentrations in their stormwater compared to natural, undeveloped areas. In fact, stormwater from agricultural and urban environments typically shows total nitrogen concentrations that are 1 to 3 times greater than what we find in stormwater originating from pristine natural landscapes. Here, we're examining typical total phosphorus concentrations found in stormwater runoff. We start with a baseline, represented by the concentrations you would typically find in a natural, undeveloped area. What's critical to observe is that all the land uses depicted show event mean concentrations, or EMCs, that are notably higher than those from natural areas. In fact, development generally results in a significant increase, ranging from a 3 to 10-fold rise in total phosphorus concentrations compared to undeveloped values. Specifically for agricultural and urban areas, the total phosphorus EMC values can be up to 10 times greater than the average concentrations observed in natural, undisturbed environments. The Natural Area Monitoring Project was initiated because the development of the statewide EMC database revealed a significant lack of data for non-developed land uses. To address this gap, the Florida Department of Environmental Protection, or FDEP, funded a project with ERD, The primary objective was to characterize runoff quality from common natural, undeveloped upland vegetative communities throughout Florida. The data gathered from this effort would then be crucial in supporting the pre-development runoff quality standards for the statewide stormwater rule. For this monitoring, state parks were utilized as the natural areas. Regarding the work efforts, a substantial undertaking involved establishing a total of 33 automated monitoring sites across 10 different state parks throughout Florida. Monitoring was systematically conducted over a 14-month period, specifically from July 2007 to August 2008. This extended timeframe was chosen to ensure the inclusion of a wide variety of seasonal conditions in the data. Ultimately, a total of 318 samples were collected during this period and meticulously analyzed for a comprehensive suite of parameters, including general water quality indicators, various nutrients, demand parameters, fecal coliform, and heavy metals. Here, we're looking at a summary of Florida's natural non-developed land use classifications, based on work by the Florida Fish and Wildlife Conservation Commission. They sampled and classified 9 distinct natural areas across the state. It's noteworthy that pinelands alone constitute about 60% of these 9 sampled areas, highlighting their prevalence. Overall, these monitored natural communities collectively represent more than 92% of all upland land covers in Florida. Our monitoring of natural area runoff and event mean concentrations was conducted across 10 state parks throughout the state. These locations covered a wide geographical range, including the Panhandle, the Peninsula, and the southern portions of the state, giving us a broad perspective on different environmental conditions. Here we're examining the characteristics of a mixed hardwood forest, similar to the type found at Alfred B. McClay Gardens State Park. This particular forest community is quite common across the northern Panhandle of Florida. It's defined by a well-developed closed canopy, forming an upland hardwood forest that typically grows on rolling hills. Interestingly, these forests generally lack species like shortleaf pine and American beech, which are more characteristic of more northern regions. The terrain itself often features these rolling hills, and beneath the surface you'll frequently find limestone or phosphatic rock close to the surface. It's in environments like these, particularly within the shallow ravines that collect and transport runoff, where field monitoring of water flow has often been conducted. Here we're looking at the Mesic Flatwoods or Pinelands community, which is a very common and widespread ecosystem throughout Florida. You might also hear it referred to as pine flatwoods, pine savanna, or even pine barrens. This community is characterized by an open canopy forest featuring widely spaced pine trees. Beneath this open canopy, there's a dense ground cover composed of various herbs and shrubs. These flatwoods typically occur on relatively flat areas that are moderately to poorly drained. The soils in these areas generally consist of 1 to 3 feet of acidic sands, which usually overlay an organic hardpan or a clayey subsoil. This particular biological community is actually the most widespread in Florida, estimated to make up anywhere from 30 to 50% of the state's uplands, truly highlighting its prevalence across the landscape. We're now looking at wet flatwoods, a fascinating ecological community also known by several common names such as low flatwoods, moist pine barren, hydric flatwoods, pond pine flatwoods, and cabbage palm pine savanna or flatwoods. This particular community has been well documented in locations like Jonathan Dickinson State Park in Martin County, which is in southeast Florida. In terms of its characteristics, wet flatwoods typically features relatively open canopy forests with scattered pine trees or cabbage palms. The terrain itself is generally quite flat and poorly drained, which is a key defining feature. The soils in these areas consist of about 1 to 3 feet of acidic sands, which lie directly over an organic hardpan or a clay layer. Here, we're looking at the upland hardwood forest, a significant ecosystem often found in places like Silver River State Park in north-central Florida. This park was actually used to document non-developed catchments that characterize this forest type. As you can see, these forests go by many different names, reflecting various regional distinctions and ecological perspectives. They're also known as Mesic hammock, climax hardwoods, or simply upland hardwoods, You might also hear them referred to as beech magnolia climax or oak magnolia climax, especially when those trees are dominant. Other common names include pine oak hickory association, southern mixed hardwoods, clay hills hammocks, and even Piedmont forest, depending on the specific location and composition. Regardless of the name, these communities share distinct characteristics. They are well-developed, closed canopy forests comprised of upland hardwoods, typically found on rolling hills. In Florida, you'll most commonly encounter these forests in the northern and central parts of the peninsula. Our focus here is on the ruderal or upland pine forest. The data we're examining for this particular forest type was collected from Lake Louisa State Park, which is located in central Florida. It's important to understand that ruderal areas refer to vegetative communities that are in a transitional phase, moving from one type to another. This specific ecosystem is also known by several other names, including longleaf pine upland forest, loblolly shortleaf upland forest, clay hills, or simply high pineland. Characteristically, you'll find a rolling forest of widely spaced pines with very few understory shrubs and a robust dense ground cover primarily made up of grasses and various herbs. This type of community typically thrives on the rolling hills found in extreme northern Florida. The soils in these areas are a mixture of sand, along with variable amounts of miocene clays. We'll now look at the Fakahatchee Strand State Park, which is located in extreme southwest Florida. This area is significant because much of the data on swamp or cypress stands was collected here. The ecosystem we're focusing on is the Strand Swamp, also known by the synonyms cypress strand or stringer. These unique communities are characterized by being shallow, forested, and typically forming elongated depressions or channels. They are dominated by bald cypress trees. Geographically, they are situated in natural troughs within a flat limestone plain. The soils in these areas consist of peat and sand overlying limestone bedrock. You'll find these particular types of strand swamps occurring mainly in Collier County. We're looking at the upland mixed forest classification, an ecological community whose defining characteristics were documented from San Felasco Hammock Preserve State Park, located just north of Ocala in central Florida. This particular forest type is known by many different names, reflecting its varied compositions and regional distinctions. You might also hear it referred to as a mesic hammock, climax hardwoods, or upland hardwoods. Other common synonyms include beech magnolia climax, oak magnolia climax, pine oak hickory association, southern mixed hardwoods, clay hills hammocks, or even Piedmont forest. In terms of its community characteristics, the upland mixed forest is typified by well-developed closed canopy forests dominated by upland hardwoods. These forests typically grow on rolling hills and are most commonly found in northern and central Peninsula Florida, specifically north of the Ocala region. Generally, these forests lack species like shortleaf pine, American beech, and other plants more commonly associated with northern climates. We're now focusing on the dry prairie ecosystem found at Miyaka River State Park, which is located in Sarasota, Florida, in the southwest central part of the state. This particular site was instrumental in documenting the environmental management characteristics for dry prairie land use that remains undeveloped. This type of habitat is also known by the synonyms of palm savanna or palmetto prairie. When we look at the community characteristics of a dry prairie, we find it's a nearly treeless plain. Instead of trees, it features a very dense ground cover, primarily consisting of wiregrass, saw palmetto, and various other grasses, herbs, and low shrubs. The terrain itself is relatively flat, and it's characterized by moderately to poorly drained conditions. The soil composition typically involves 1 to 3 feet of acidic sands, which generally overlay an organic hardpan or a clayey subsoil. Here, we're focusing on the xeric scrub community, using Wekiva River State Park as a key example. This park was specifically utilized to document the event mean concentration, or EMC, for these particular scrub areas. You might also hear xeric scrub referred to by several other names, such as sandpine scrub, Florida scrub, sand scrub, rosemary scrub, or oak scrub. These communities are characterized by a canopy that can range from closed to more open, typically dominated by sand pines. Below this canopy, the understory is quite dense, featuring thickets of scrub oaks and other shrubs. Geographically, you'll find these scrubs on sand ridges, often remnants of ancient shorelines. A crucial characteristic is their well-washed, deep sandy soils. This leads to them being extremely well-drained, to the point where they typically only generate surface runoff during very substantial rain events, generally 2 inches or more. When selecting our monitoring sites at Silver River State Park, we focused on understanding the natural communities present, specifically the upland hardwood areas. A key aspect of this process is that natural communities are extensively mapped and documented across all Florida state parks. This means we have clear delineations of community types available, allowing us to easily assign the specific vegetation community for any given site. For our particular study, we identified potential monitoring sites within these communities of interest. The critical selection criterion was to choose locations where runoff naturally converges into a conveyance channel, which is essential for accommodating our field monitoring equipment and methodologies. Finally, to ensure accuracy, we plotted the exact coordinates of our selected sites onto a GIS map of community areas, which was developed by the Florida Department of Environmental Protection, to verify their placement within the correct natural community. These geometric mean values summarize the runoff characteristics we observed across the 14 monitored natural community types. It's important to note that natural areas frequently showed violations of the Class 3 criteria, particularly for both iron and fecal coliform bacteria, with their overall geometric mean concentrations exceeding the applicable standards at multiple sites. Additionally, we found that nutrient concentrations, especially for total phosphorus, were highly variable between these different community types. Interestingly, total phosphorus concentrations in several natural areas, particularly those with deciduous forests, actually exceeded the event mean concentrations observed in some developed areas. When we consider identifying natural vegetation covers for potential development projects, several indices are available. One of the earliest and most comprehensive is the Florida Vegetation and Land Cover, often referred to as FFWCC. This program is part of Florida's Natural Heritage Program at Florida State University. The FFWCC survey is designed to reflect existing land cover across the state, based on detailed aerial photography encompassing both developed and natural areas. The original survey, conducted in the 1990s, identified 17 natural and semi-natural cover types, along with 4 types reflecting disturbed land and a single water class. The survey was significantly updated using 2003 aerial photography, which led to a much more detailed classification. This updated version identified 26 natural and semi-natural cover types, expanded to 16 land cover types reflecting disturbed land, and maintained the water class. Coverage maps from this survey are available for all of Florida, providing invaluable data. While extremely useful, it's important to remember that the data is subject to the inherent limitations of aerial photography. A digital GIS version of this updated survey was released in 2004, making it widely accessible for various analyses. Another natural community index we'll discuss is the Florida Natural Areas Inventory, or FNAI. This system was developed by the Florida Department of Natural Resources and is widely used by the state park system to classify and understand natural areas. FNAI reflects the original natural vegetation associations found across Florida. Natural communities within this system are characterized and defined by a combination of several factors: physiognomy, vegetation structure and composition, topography, landform, substrate, soil moisture conditions, climate, and the influence of fire. Each community is then named for its most characteristic biological or physical feature. These communities are organized hierarchically, grouped into 6 natural community categories, which further break down into 13 natural community groups, and then 66 specific subgroups, primarily differentiated by their hydrology and vegetation. While detailed coverage maps may not be uniformly available for every single part of Florida, The FNAI system itself provides a comprehensive framework applicable statewide. For our natural area characterization study, this FNAI coverage index was specifically selected for its robust methodology. Moving on to our third natural community index, we have the Florida Cooperative Land Cover Map. This important resource was initially released in July of 2010 and has since been updated, with version 3.5 coming out in November 2021. What makes this map particularly valuable is its comprehensive nature. It combines aspects of both the Florida vegetation and land cover data from FFWCC and the Florida Natural Areas Inventory, or FNAI. This integration provides a much richer and more detailed picture of land cover across the state. For practical application, it's readily available in GIS format, making it an accessible tool for researchers and land managers. The Florida Fish and Wildlife Conservation Commission, FWC, holds primary responsibility for this map, with significant assistance from the Florida Natural Areas Inventory. We're now looking at updates to the natural community indices, specifically concerning the Florida Land Cover Classification System, often referred to as FLUX. The Florida Department of Environmental Protection, or FDEP, has initiated an important evaluation to develop a more unified lake cover classification system. This system, which was last updated in 2012 and 2018, currently identifies 22 distinct terrestrial and wetland types across the state. The goal of this FDEP initiative is to create a more robust classification system. This new approach will better account for subtle spatial differences that exist within these classifications and incorporate natural community indices. This involves a comprehensive revision of the existing GIS layers. While it will remain a numbered classification system, similar in structure to FLUCCS, the actual numbers themselves will be different, reflecting the updated categories. The expectation is that this system will be updated frequently to maintain its accuracy and utility. This work is part of FDEP's broader efforts in managing statewide land use land cover data. When we're dealing with loading calculations, we often utilize FLUCCS codes. FLUCCS stands for the Florida Land Cover Classification System. These codes are used on maps to give detailed descriptions of various land covers and uses, which is fundamental for identifying the specific land use needed to determine the event mean concentration, or EMC, in our models. However, there are a couple of significant problems when directly applying FLUCCS codes for runoff modeling. First, the FLUCCS codes often contain an excessive amount of detail, which can sometimes lead to misclassification of land use activities for modeling purposes. Second, and critically, we simply do not have runoff event mean concentration data available for every single one of the many listed FLUCCS land use categories. To address these issues, the FLUCCS codes have been carefully converted into a set of closer, more general categories. This conversion is based on the anticipated runoff characteristics of the different land cover types, making them more suitable and practical for modeling. This converted set of categories is readily available for use within the BMPFast model. Let's take a moment to recap what we've covered in this section. We started by understanding how a land use is defined, often with the help of publications like those in the FLUCCS manual. We then delved into how event mean concentration, or EMC, values are determined. We learned that this data is based on extensive field data collection, drawing from dozens of studies. This rigorous sampling for runoff volume and concentration data was crucial and reflects the high level of accuracy needed to determine annual average EMC values and the overall pollutant mass of discharge. Finally, remember that you can find a comprehensive listing of acceptable EMC values in the Applicant's Handbook, Volume 1, Table 9.2, which was published by FDEP in June 2024. This concludes our module on runoff characteristics and EMC values. We encourage you to visit our other learning modules to further your understanding and to learn how to take the competency test by viewing the self-test learning module. Thank you for watching.